Assalamualaikum and good morning. I'm Dr. Sabah Bau from the Physics section, Pusat Pengajian Pendidikan Jarak Jauh, University Science Malaysia. This is course JIF 318 Quantum Mechanics. We are now in chapter 2, Complex Numbers and Linear Operators. This segment, unit 2.1, is on the Cartesian complex number. Remember that Cartesian is basically the three-dimensional world we are in, which can be explained in terms of the axis x, y, z. After this lesson, hopefully you can define and identify complex numbers, and also you will be able to do some mathematical operation involving complex numbers. Quantum mechanics marks the entry of complex numbers in a fundamental way into physics. That means, in quantum mechanics, you cannot run away from complex number. As the statement says, in a fundamental way. That means quantum mechanics is closely related with the applications of complex numbers operation or formulation. So complex numbers arise when we try to take the square root of negative numbers. Okay, in the secondary school days, in lower mathematics, you can see that you cannot square root the negative numbers. And usually during that time, our teacher will say the solution is imaginary. That means it is not real. Even in some, if you are have studied additional mathematics, we have also touched on complex numbers. Basically, this is the definition for complex numbers. If you want to square root a negative numbers, basically, even if you use your calculator, then your calculator will give up, saying no solution. But for mathematical operations in quantum mechanics, we replace the square root negative numbers with a letter of small I. So generally, a complex number Z is the sum of a real number A and imaginary number Bi. Okay, so this is how you present a number which is called a complex numbers. A is the real numbers and B is the imaginary numbers. The properties of this relationship or expression is that if B equal to 0, then Z is wholly real. Of course, if B equal to 0, Z will be equal to A and A is real. If A equal to 0, then Z is wholly imaginary. If A equal to 0, then what is left? Z equal to Bi. That means Z is now wholly imaginary. A complex number Z is 0 if and only if A equal to B equal to 0. That means both A and B equal to 0, only then Z is 0. Sometimes it is convenient to think of Z or a complex number as occupying a two-dimensional number plane. That means a plate to the graph like this. It's called Argand diagram. Okay. Basically, we have the x-axis is marked as real axis and y-axis as imaginary axis. So if we want to write down a complex number, 3 plus 4i. 3 here is a real number and 4i is the imaginary number. So in this plot, basically, 3 is the component of the real axis and 4i is the component for the imaginary axis. So you can draw an arrow from the origin here to that point, 3 plus 4i. The same thing, for example, if you are given a complex number, negative 3 minus 2i, then negative 3 is the component with respect to the real axis, and negative 2i is the component with respect to the imaginary axis. So you can plot an arrow from the origin to that spot, okay, to that coordinate. That's how you try to visualize complex numbers. You can try this with other complex numbers. Sometimes people ask, how come we have this negative square root of negative numbers? Is it possible to have square root of negative numbers? If we are given a quadratic equation like this, z squared plus z plus I, so this equals to 0. So this is a quadratic equation. The solution of the quadratic equation is z equal to negative b squared, where b is the the coefficient of z, plus minus square root b squared, now 1 squared, minus 4ac. That's the general formula for the numerator. But a is 1, a is the coefficient for z squared, and c is the constant here. So negative 4ac, 4 times 1 times 1. So we have this. Divide by 2a, where a is the coefficient of z squared. So the denominator is 2. So 1 minus 4 in the square root, you can see here square root negative 3. Then now we have these complex numbers. Negative 1 plus minus square root negative 3 divided by 2. Okay, so how are we going to replace the negative 1 inside the square root? We replace it with an I here. Okay, so now you can solve the equation, except that that means square root 3 you can definitely find it by using your calculator, but you have a letter I indicating that square root 3, that is the number there, is multiplied by I, and the whole thing here, I square root 3 is basically the imaginary part of the complex numbers. So z now is a complex numbers because of the presence of I in the expression. Equality. When two complex numbers are equal, the real and imaginary parts can be equated. Remember that if two complex numbers are equal, the real and imaginary part can be equated. If, let's say, we have a complex number s plus ic, so here it is defined or equal to exponential x inside the bracket cos x plus I sin x plus exponential negative to the power of negative x, okay, inside the bracket sin x plus I cos x. Then you can see here that if we rearrange the right hand side, you can see cos x multiplied by ex, and here sin x multiplied by negative x are real numbers, because these two expressions does not contain any I. So we can define s is the one without the I, you can see here. So we can define s equal to ex cos x plus exponential negative x sin x. While here I sin x multiply with exponential x, and negative cos x here multiply with the exponential negative x. So this will be your C, because those expression have I, so IC must be equal to those expression containing I. So C equal to ex sin x plus exponential negative x cos x. Okay. Addition. What about addition operation for complex numbers? If z1 equal to a1 plus ib1 and z2 equal to a2 plus ib2, then if you add z1 plus z2, basically you just add whatever being there. That means a1 plus ib1 plus a2 plus ib2. Then you can rearrange, because a1 and a2 are real numbers, so the real numbers first, that's mean in the bracket A1 plus A2, and then you have the imaginary numbers B1 plus B2 multiplied by I. You can imagine or visualize what this means from the Argand diagram. Again, Argand diagram, x-axis is real and y-axis is imaginary. Okay, so let's say if P1 just now as defined here Z, but now we try using P. If P1 is A1, even though this is just coordinate, but we know that actually this is equal to A1 plus B1I, because the B is with respect to the y-axis, which is the imaginary axis. And the same with P2, that means when we plot Py, we know that for P1, A is A1, that's the real number. Then the imaginary one, this is B1. And for P2, A2, and the imaginary part is B2. So when we add, basically, we add the real numbers with real numbers. Okay, that means A1 plus A2, and the imaginary numbers with imaginary numbers B1 plus B2. So the position here for P3, that means the total is A1 plus A2. That's basically you add A1 and A2, and that's is the value here. Okay, A1 plus A2. Okay, A1, that's mean from origin to the position of A1, then from the plus from the origin to the distance from the origin to the A2 is equal to A1 plus A2. That means you add these two, so that will give you the distance to the real numbers of P3. The same thing with the imaginary parts of P3. Subtraction, again, this is direct subtraction. Just like the addition, you put the negative sign among the or between the bracket there, then you rearrange to get the real number. First A minus C, then the imaginary number second B minus D. Okay, this is the Argand diagram to show or to visualize Z1 minus Z2. Okay, as usual, the axis is the real axis, y-axis is the imaginary axis. Z1, as you can see here, Z1 and Z2 both are positive. That means in the same quadrant. Let's say Z1 is here, Z2 is here. But when we do the operation Z minus Z1, Z1 minus Z2, that means now Z2 is negative. If Z1 in the first quadrant is positive, then negative Z2 should be in opposite of the first quadrant. That means in the third quadrant. Okay, so Z1 minus Z2 is the resultant is here. Okay, that means that I think you are familiar with what you call it, the resultant of vectors in the lower levels. So Z1 minus Z2 is here. Okay, because minus Z2 is here. No, it is opposite of the positive Z2. Okay, what about multiplication? Again, if we have Z1, Z2 defined as before, when we multiply, we use the same usual method. I mean, the first multiply by first multiply by second, then the second multiply by first, then second multiply by second, as we did usually in the lower level when we have multiplication in brackets like this. Okay, so we have AC plus BCI, that means imaginary, plus ADI, imaginary, plus BDI multiplied by I. Okay, remember that I multiplied by I is I squared. It is equal to negative 1. Remember that square root negative 1 is equal to I. Therefore, I squared must be equal to negative 1. So here, the symbol before BD should be changed to negative. So we rearrange. The real number is AC minus BD, and the imaginary number is BC plus AD. For division is more subtle. That means there is a little trick on it. Okay, Z1 minus Z2 is actually A plus B1, BI divided by C plus DI. So the trick is that we try to make the denominator real. That means no I for the denominator. How to do it? If you have denominator C plus DI, then you multiply with C minus DI. Because when you multiply out C plus DI, multiply by C minus DI, so finally what you have is C squared plus D squared. There is no imaginary part there, no I there. So if you multiply the denominator with C minus DI, the top or numerator should also be multiplied by C minus DI. So the top one you multiply and you have the imaginary part there. The real part is AC plus BD plus the imaginary part I in bracket BC minus AD. But the denominator is C squared plus D squared is real number. So again, as a whole, you can see that the equation is or consists of real part and imaginary part. An example, for example, here question express 2I, here this slash here is actually divided by 1 plus I in the form of A plus IB. That means in the form of a complex number. So this is the division just now, okay? You have 2 plus I divided by 1 plus I. In order to make the numerator or denominator real, if you have 1 plus I, then you must multiply 1 minus I. When you multiply the denominator with 1 minus I, the numerator must also be multiplied by 1 minus I. So again, you can see here that you have I squared here, which is equal to negative 1. So negative 1 multiplied by negative here must be positive 1. That's why finally you have 2 at the bottom here, while negative I plus I will be 0. So you have 3 minus I divided by 2 in the form of A plus IB. That means the half will be outside of the bracket. 3 minus I. 3 is the real number, and 1 here should be the imaginary number. Cube roots of unity. Okay, remember that when in the lower levels, when you have cube root or square root, it's quite easy. It is positive or negative. But when cube root, how you did it? Okay, usually if we have, for example, z cube equal to 1, or if we rearrange z cube minus 1 equal to 0, so we usually factorize. Okay, we factorize into this. Okay, this expression z squared plus z plus 1 is a quadratic equation. Then z minus 1 is another expression there. You multiply both expression equal to 0. So the first part is okay. I mean, in order to get 0 on the right here, either z minus 1 equal to 0 multiplied by this equal to 0, or z minus 1 here is there, and z squared plus z plus 1 must be 0. So z minus 1 multiplied by 0 also 0. So there are, in this case, it looks like 2 possibilities. Of course, the first one, if z minus 1 equal to 0, then z must be equal to 1. So z equal to 1 minus 1 is 0, multiplied by the second expression must be equal to 0. In the second case, okay, the second expression should be 0. Z squared plus z plus 1 equal to 0. Just now we had solved this, okay, using quadratic equation. So we have the expression it is complex numbers. So for this simple expression or simple formula z cube equal to 1, actually we have 3 roots. Okay, the cube roots of unity are, so we have these roots. The first one is 1 here, the first expression, and the second expression give you another two roots. Okay, so the roots for the z cube equal to 1 is 1. The second one is half in the bracket minus 1 plus I third 3 or square root 3. This is the second root. The third root is half in the bracket negative 1 minus I multiplied by square root 3. Okay, so you can see that you can solve this equation involving cube root. Okay, in the secondary school, usually when it involve square root of negative, we said that it is unacceptable or imaginary only. But now we can really solve it, except that for the imaginary part we have the letter I. In conclusion, a complex number consists of real and imaginary parts. A complex number may be represented by an Argand diagram. I think you have to familiarize yourself with this diagram. And real-life mathematical operation may involve complex numbers, especially in quantum mechanics. Thank you very much for your attention.